Good morning, everyone. I welcome you all to this virtual CDE program on sample size calculation and sampling techniques on behalf of Team Public Health Dentistry, Vivekananda Dental College for Women. Before we start with the proceedings, I would like to convey our sincere gratitude to our beloved Dean Sir, Captain Dr. Gopalnathan Sir, our Principal Dr. Balan Sir, our Head of the Department Dr. Girish Sir, the Orator of the Day Dr. Sangeeta Chavan Ma'am, Head of all the other departments, beloved faculty members, postgraduates and interns for having your presence here today. I request all the participants to kindly mute yourself and help us in conducting the program effortlessly. You are free to post your queries in the chat box and the same will be addressed at the end of the session. Now I take the honor in introducing our guest speaker for today, Dr. Sangeeta Chavan Ma'am. She is currently working as a professor in the Department of Public Health Dentistry, Best Dental Science College, Madurai. She completed her BDS from KLE, Belgaum, MDS from Babuji Dental College, Davangere. She has also done postgraduate diploma in medical legal systems from Symbiosis, Pune. She has keen interest in biostatistics and research with more than 25 publications in national and international journals. She is currently resource person in various colleges. I'm happy to welcome you, ma'am. The stage is all yours.
Yeah, now it's fine.
Am I audible?
Yeah, you are audible, Sangeeta.
Right. Okay, so we have to rely on something known as sample. Okay. So what is sample? Sample is a small representation of the entire population. So whatever data we collect from a sample get extrapolated to the population. For example, when we generally go, during the mango season, when we go to buy mango, and imagine if you're buying a whole basket of mango, you just check 2 or 3 mangoes, maybe in the front row, in the middle row, and the bottom. But that doesn't mean that you're just taking those 3 or 4 mangoes and going back home, right? You're taking the entire basket, because if those 3 mangoes are good, your interpretation for that is that entire basket is filled with good mangoes. The same thing applies when we are talking with respect to sample. When you are doing a study and proving something in a sample, we are extrapolating that to the population. Same thing when even you go and buy a sack of rice. You don't need to check every grain of rice, because if you do that, imagine the time and resource you're going to spend. So this is the importance of the sample. So we need a sample because doing a study on the universe, that is the entire population, is very, very tedious job. You know, when census is conducted, there is so much of background data, so much of manpower resources that goes into it, right? Supervision of study subjects, when you do in a very, very large population or the whole population, it is very difficult to supervise. Obviously, money. It's very expensive when you do a study on the whole population. And when you're doing a study on a sample, you get quicker results. So what happens when the results are quick, the application is quick. You know, the COVID vaccine that came, so it doesn't mean they have tried the COVID on each and every person, vaccine, right? They tried it on a sample. When it was proved useful, they gave it to the entire population. So a sample needs to have certain ideal requisites. The size should be adequate, it should be feasible, it should be cost effective. Above all, it should be a representative sample. The next question that all people wonder, how many should I take when I want to sample, and how should I collect the sample? So these two are the questions that I shall be answering today. How is through sampling methods, how many, a very systematic sample size calculation method. So I am dealing right now with the first part, and that is the sample size, the number of population or the number of participants or subjects that you need in your study. how are you going to derive this? But before I answer how we are going to derive it, why we need a sample size? Again, it's very similar answer, like why we need a sample, right? Too small a sample. First of all, even if your two things that you're going to test is significantly different, you may not be able to find that difference. Okay, so you may have a false positive, a false negative when you have a smaller sample size. Apart from that, a smaller sample size may not give you the total representation of the population. Imagine if I am going to try to take your feedback about how you are feeling my presentation, and I just pick up 2, and for my bad luck or good luck, those 2 are the PGs. So obviously their understanding is better. So with that, I may conclude, and my result is not the actual result. Okay, so too small a sample size will fail to give the difference. Secondly, your results are inconclusive. And third, it doesn't give you or provide you a representation of the entire population. So what? We'll go for the larger. But it is not that always the larger the better. It doesn't actually follow here. If you take excessively large sample, even then you can get a false positive result. There are chances of getting a false positive result. Apart from that, it's expensive, tedious, and obviously waste of time and money. Okay, so we need to strike a balance that is not low, a balance that is not high. So in mediate that the sample size is just adequate to serve the purpose and answer our research question. Small example here. So imagine if I give this particular box to someone among you, and you, without opening the cover, just take out one sweet from this part of the box. And yes, you say, oh, this box has the apple sweets in it. And then I said, okay, try one more. And you take out the sweet from the other part. And you say, it's a watermelon sweet. So with this, you may conclude that the box has, 50% of watermelon and 50% of your apple sweet. But in reality, it contains much more than that. So the way you sample and how much you sample is very, very important. What are the steps of calculating the sample size for a particular study design? So these are the major steps, which include you have to specify the hypothesis, you have to specify the significance level. Next, the effect size, the intended power of the test, and ultimately know the test that you need to apply to calculate the study. Calculate the sample size. Okay. In this presentation, I'll give you a demonstration of the G Power software, which is used very commonly these days to calculate sample size. So moving ahead with the first one. Okay. So apart from this, the other factors that you need to consider are the dropout. What happens is that whenever we are doing a longitudinal study, a prospective study, you start with 100 people in your study, okay, 100 subjects in your study. Over a period of 6 months, you see hardly 40 or 50 are coming back to you. You need to anticipate this dropout before you start your study, and then do the adjustments. That is, you have to add these extra dropout rates or percentage of people in your sample size calculation. You should also consider if they are like 2-group study or more than 2-group study, what is the ratio of allocation of subjects in each group. If there is unequal ratio, then obviously it will affect your sample size calculation. Okay, and next is the object. Moving ahead with our first step, that is to specify a hypothesis. What is an hypothesis? An hypothesis is an assumption or presumption that you have to make. Okay, it's a statement that either you have to prove or disprove. Okay, most of the time, most know majority of the time, you always start with null hypothesis. It is like the case going in the court, right? A person is considered innocent unless proved guilty. Same thing here. You have to start believing your null hypothesis unless the null hypothesis is rejected. Clear? So what is the null hypothesis? Null hypothesis is just nullifying everything. If you're trying two new products, that is A and B, just say both are same, treat them similarly. Okay. If you have the concept like A is better than B, obviously you have a predilection towards A. So always start by considering both as equal. So that is null hypothesis. In contrary, you have to also present an alternative hypothesis, which is what difference are you anticipating? It is just like opposite to null hypothesis. If null hypothesis is saying A and B are same, your research or your alternative hypothesis says A and B are not equal. Okay. Moving with the small examples to make it much more clear to you. If I have a study suggesting that toothbrushing has an effect or not, doesn't have an effect on dental caries. So my null hypothesis will using toothbrush has no effect on the prevalence of dental caries. So what will be my research hypothesis? It does have an effect. Now just one more point to remember here. I am saying it has an effect. I am not saying that it is reducing the prevalence. Neither am I saying that it's increasing the prevalence. I'm playing a double game here. So this type of hypothesis are non-directional hypothesis. I'm emphasizing because this thing you may need in your sample size calculation. When you have a non-directional hypothesis, you need to use a two-tailed test. Okay, please remember, when it's a non-directional hypothesis, you need to use a two-tailed test. Next example, drinking coffee has no effect on systolic blood pressure. This is obviously my null hypothesis. My research is drinking coffee has an adverse effect on systolic blood pressure. Okay. Now what am I doing? I am saying what type of effect. It has an adverse effect. So rather than playing a double game, I'm shifted into one particular party. I'm telling it has an adverse. I'm not saying it just has an effect. I have, supporting that it has a bad effect. So it is a directional hypothesis. So whenever you have a directional hypothesis, you have to use one-tailed test. Okay. So this is an example for that, like one-tailed and two-tailed. This is a normal distribution. As I said, it is a statement that should be refuted or accepted. That is hypothesis. But this guy's love is not hypothesis. It's a theory. It will stand still as much as much ever time you test it. Okay. Moving ahead with the next step. That is to specify the significance level. I shall be dealing two things together, the significance level and the power. Okay. The significance level we all know is a p-value, right? So everything, I can make it very clear through this one particular slide. If we are doing any study, okay, see there is something that is really existing. If I have to say that drug A is better than drug B, okay, this is the reality, that drug A is invariably better than drug B. So what can happen? I can get a result like, yes, drug A is better than drug B. Okay, so that is drug A is better than drug B. I am rejecting the null hypothesis which says both are safe. Okay, so my result is right. Okay. Sometimes it happens that A and B in reality both are safe. But your study result shows that A is better than B. Okay. We are saying both are same in actual. In real, both are just the same. But when you do a study, you prove that one is better than the other. You are rejecting a null hypothesis when it is true. Okay? Okay. Was there any confusion related to this part? Fine. I'll do one thing. There is a small little clip picture next to this slide. I'll just show you all that first and then get back to this slide. Fine. See, here, what is the reality? What is the reality? This particular man is not pregnant. Obvious that is, right? That is the reality. But what is the doctor saying? He is making some error. He is going away from the error. That is, he is telling something which is false positive. Right? That's type 1 error. Fine. Here, it is so obvious that the lady is pregnant. She is pregnant. But what is the doctor saying? That you're not. So obviously, they are creating an error. This is type 2 error. Okay. Identifying a disease when it is not actually present or a condition which is not actually present is your type 1 error. And not identifying the problem when it is present, that is giving a false negative, that is your type 2 error. Okay. I hope this image really makes the things clear. I would appreciate if people would respond in the chat box so that I know that I'm clear with the concept.
Ma'am, I'm getting a direct message from some participants that it is clear, ma'am. The concept is clear. Yes.
Okay. Thank you. Right. So we have dealt with what is type 1 error. Okay. And what is type 2 error. And when we find the truth, no difference, you also identify no difference. Truth. Very good. Okay. There is a difference. You also identify there is a difference. Again, it's a truth. Again, very good result. Okay. So no research can be conducted without having these errors. Frankly speaking about it, you cannot conduct a research which is 100% proof, right? But we can allow a minor error, but we have to prevent blunders. That is what should be our concept when we are conducting research. So how much of type 1 error are you allowing? How much is okay for you? Okay. Rejecting of null hypothesis when it is true. That is your type 1 error. And actually, there is no difference, but you are saying that there is a difference. To what percentage? And we fix this to 0.05. Okay. And this is your significance level. So whenever we say this P is equal to less than 0.05, means you are allowing how much percent of type 1 error? 5% of type 1. Right? How much percentage of type 2 error are you allowing? That is when there is a difference. You are saying there is no difference. Okay. When there is an actual difference between A and B, and you are saying there is no difference. you are giving a false negative result. How much are you accepting? So 20% is what is an acceptable error, right? So the type 1, we call it as alpha error, and type 2, we call it as beta error. The counterpart of alpha error, that is 1 minus alpha. So if you're fixing it up at 5%, the rest 95% is nothing but your confidence level. Okay? With so much of confidence, you are saying, that is 95% of confidence, you are saying that I am going to accept the null hypothesis when it is true. That means if A and B don't have any difference, my research is also going to identify the same 95% of time. Okay? That is your confidence. With how much of confidence you are accepting the null hypothesis when it is true. And the contrary to the beta error is your power of the study. The ability to reject the null hypothesis, okay, to reject the null hypothesis when it is false. Okay. So that is the power of the study. So in this particular slide, we have said what is an alpha, which is nothing but a significance level. The contrary to the alpha is a confidence. To identify true negative. To identify true positive is a power of the study. And then you have a beta error. Which is false negative. Clear? Okay. I'm just going through the queries. I will answer each one of them. Okay. Coming to the probability, that is what I said, that it ranges from 0 to 1. So we generally fix it at 0.05. Now this is an arbitrary fixing. It is not that every time you have to fix the significance level at 0.05 only. Okay. You can also reduce it to 0.001. Many of the drug trials, when they want to be very, very sure about their result, they go for 0.001 also. So it is based on you, what significance level or how much of type 1 error can you allow in your study. If P is low, then null hypothesis has to go. Okay. So whenever you have P of less than 0.05, that means you are rejecting the null hypothesis. So obviously you are accepting the research hypothesis. Power of the study, I have already dealt. Okay. So right now what we have completed is significance level, the power, right? So moving to the next one, that is expected effect size. Now, what is expected effect size? It is the difference what we are trying to measure between the two things. Okay, that is the difference that we are trying to measure between the two things. That is the effect size. Now, from where do we get this effect size? Through prior studies, which we call it as a key article, or by conducting a pilot study. You understand that this is the difference that you are expecting or looking for. If I have to say the height of, height, difference in the height between Chinese and Indians, and even in Indians, if I'm comparing it with Punjabis. So obviously, you know, those Chinese are really stout and Punjabis are really tall. So the effect size is more here. The difference is more. Okay. But if I have to compare Chinese and Japanese, I sometimes really don't understand. The difference is so less. That time your sample size is more. Okay. So effect size plays a very, very important. I've quoted an example here. See, now if I have to see for the aesthetic appealment of two composite restorations, say one is the dual pure, another is the light pure. Now both are composites. So how much of difference can you really expect? So if you really want to understand that difference, your sample size will increase because your effect size is very less. But if I have to compare the color changes with miracle mix and amalgam restoration, it's very, very obvious. So effect size has increased, so sample size will reduce. Okay. So we have completed with significance level, power, hypothesis, and effect size. So 4 steps are done. Next very important criteria when you're doing an observational study is that you need to know the rate of event that is occurring in the population. That is nothing but your prevalence rate. What is the prevalence of that particular disease in the population? Okay, you should know that to calculate the sample size. Again, this prevalence you can get from your previous research articles. If it is not available, you have to do a pilot study to understand the prevalence rate. Standard deviation means the variation that we are seeing in the population. The more the heterogeneous, the more the sample size. The more the homogeneous, the lesser the sample size. Like the example that I quoted earlier about rice, because rice is throughout the same, it's going to be homogeneous in the entire sack. So a little of rice, when you see, you will get an idea about the entire rice in that sack. Okay. So I shall be dealing with sample size calculation using this particular software, which is the G Power software. Now, if you see here, okay, where my cursor is just going, so we have dealt with tails. This is nothing but our first component, that is hypothesis, whether it is one-tailed or two-tailed, because we need it as our input parameter. We have done with our effect size, alpha error, that is your significance level, and the power of the study. It also needs us to give input about which test you need to apply. So we need to have a brief knowledge about which test to apply in which situation. Before I tell you about the various tests, this is a concept that we need to little bit know about the normal distribution. What is a normal distribution? In simple words, around 68% of the population lies in and around mean. Okay, it's all around mean. So there is no deviation. Here, I'll just quote an example. Like say, if there is, if I've taken 10 people, hypothetical example. So if I have 10 people, out of which 8 have height somewhere around 5.3 to 5.4. And there are 1 or 2 which have the extreme heights, say 6 or 1 has 4. Okay, then it is a normal distribution. But if the same example, okay, but only 6 people or 7 people are having a height of 5.3, 5.4, 5.3, 5.4. 7 people have this height. And 3 people have a height of 6 feet. So when I calculate this mean for this, mean means add up everybody's height and divide it by 10. Right? So if I calculate the mean, I will get the mean somewhere around 5.5 and 5.6. But what has happened? 7 people are below this mean. Okay? 7 people are below and only 3 people you have above this level. So this is a skewed distribution. So if you can understand this concept, that's more than enough. What is a normal distribution? What is a skewed distribution? We have different type of study design. So this is a slide which simplifies the various study design which are most commonly used. See, there are study design beside what I have even shown here, but I have just picked up the most common one. So this particular diagram here represents the groups used in our research design. So if there is a single group, okay, So you can use one of these tests. Now, how are you going to decide which test to use? If it is a normal distribution, go for parametric. If it is a non-normal distribution, go for a non-parametric. Simple. Non-non. Okay. So if it is a normal distribution, go for parametric. If it's a non-normal distribution, go for a non-parametric. Now, the next question that arises, how are we going to understand? Yes. Sometimes in your key article, in the analysis section, they would have mentioned that it follows a normal or a non-normal distribution. Please remember, we are talking about sample size calculation and not test of significance. Okay. For sample size calculation, you will have to rely on the key article. In the key article, they would have mentioned somewhere that the data has followed a parametric or a non-parametric distribution. Okay. What if they have not mentioned? Yes, there is a solution. You have to see for the standard deviation. Okay. If the standard deviation is very large, you know, the mean plus or minus. So if mean is say 4 and standard deviation is plus or minus 3.5. Okay, so it's a very, very wide range. So that time you can assume that it is a non-normal distribution or a skewed distribution. Is that clear? How to find out between a parametric and a non-parametric test, for which we will need to understand a normal or a skewed distribution. Okay. There are various tests. Okay. When you are doing a research and then you want to check, that is a different issue. But when it is with respect to sample size calculation, you have to rely on your key article data alone. Key article data, or if you are doing, say, pilot study, then even on the pilot study data you can rely. When you are doing a pilot study, you have the data for all your observations, means all your the subjects who are involved in the study, right? So if I am taking 20 people in my pilot study, I have data for all the 20 people, but key article will not give me. So when you are doing a pilot study and you want to check whether the data is normal or non-normal, you can apply Kolmogorov-Smirnov test or Shapiro-Wilk test in SPSS, which is actually beyond the scope of this particular lecture. Okay. So, but for right now, we can only understand that we have to check the normal or the non-normal distribution based on a key article. Okay. So the first example is a single group. You are doing pre-test and post-test. Okay. Like, say, pranayam, whether pranayam is having an effect on the heart rate. Okay, so you are checking the heart rate before and post the pranayam. So this is a single group study, right? So if it is a following a normal distribution, we are going to take parametric test. If it is following a non-normal distribution, you take a non-parametric test. Clear? Under parametric, it is called as paired t-test. Now, why it is called paired? Because you have two observations from a single subject. One person, you are taking his heart rate at the baseline and the same person's heart rate post-intervention. Clear? Yes. The other scenario is when you have two groups. I want to compare pranayam versus Zumba. Okay? These are the two. So in both the groups, in pranayam group also I've checked the heart rate, in the Zumba group also I've checked the heart rate. And I've told them to do their particular activities for the next 1 week time, and then again I check for their heart rate. So this type of study where you have two groups, in a parametric you have to use your t-test, unpaired t-test, and under your non-parametric you're supposed to use your Mann-Whitney test. Clear? Under G power, it is under the name of Wilcoxon only, but only difference is dependent group or independent group. So you can call Mann-Whitney as Wilcoxon test for independent group, because both the groups are independent of each other. Clear? Certain times you have three groups also. So let us say your pranayam, your Zumba, and say any other form of exercise like say aerobics. Okay, and you are comparing all three of this. So under parametric, you have ANOVA. Under non-parametric, you have something known as crystal values. Again, there is a kind of corrections in G power for crystal values. I'll let you all know about it. Okay. What if you have single group, say only the pranayam group, and you're checking them at baseline, after 1 month, and after 6 months? You have multiple recordings here. So this, you see, there's a single group. You're taking them at baseline, at intermediate, and post-test. So under parametric, you have the repeated measure ANOVA. Under non-parametric, you have the Friedman test. Okay. Sometimes we try to say the correlation. Okay. The longer the lecture hours, the more drowsy the students are. See, there is a kind of a relation. And when we are going to check such type of correlation, and if it's a parametric test that you're applying, it is Pearson's. For a non-parametric, it is Spearman. I request you all to just take a screenshot and keep this test with you all, because I'll be asking you all to tell me which test to apply when I'm doing the G power, using the G power software, right? So this is a parametric test that we want to apply. I hope all of you know this particular person. Okay. I don't know. I really had to find out. He is STI. Okay. So everybody, I heard it's a viral sensation about his weight loss journey. So it's the same subject before and after. So which test are we going to apply? My further slides will be in this mode only. So let us take an example here. Bone dimensional changes after placing of an implant, right? So we are seeing for the vertical buccal bone height. Okay, at baseline and after 6 months. We are checking for vertical bone height. So how are we going to do this? So we are going to open our G Power software. Everybody can download it. It's freely available on internet. Okay. First, go to the test. What we are checking the mean value. So we are going into mean, right? In this, we are checking for dependent groups. That is nothing but your paired T test. Okay. We are seeing for two dependent because it is the same group that is continuing. We are going to select this. If you just select this, you see here, you have a test family T test. And we are checking for the difference between two dependent groups. Under type of power analysis, you have to select a priori. Now, what is a priori? It is a sample size calculation before you do a study. Right? Whereas, after you do a study with a particular sample size and you want to know how much of power your study has, that you can calculate by selecting this post hoc. So today's, I'm just restricting to a pi. Okay. Okay. Then I have to select whether it is one-tailed or two-tailed. Now this is based on your hypothesis that you write in your synopsis. Right? Whenever you are writing your research protocol, you would have written your research question and your hypothesis. So you have to select whether it is one-tailed or two-tailed, which is decided based on its directionality, whether it is directional or non-directional. So I'm selecting two-tailed. Effect size. Now there, I told you the effect size you have to calculate from your key article. I have shown you the article. So we'll just calculate from there. Alpha error, that is your p-value. I'm fixing it at 0.05. Okay, this is the probability of committing type 1 error. Okay, power, you can, 80% is acceptable. So I just write it as 80% here. Clear? Now we will calculate the effect size. So I just see this effect size. I've just determined effect size. Okay. So I have to enter the mean. Okay. So what was the mean values in the research article? So immediately it was 1.58. Okay, that's your baseline value. And after 6 months, what was the value? It was 0.89. The standard deviation for the first group, that is your baseline, was 0.48, and for the next was 0.42. I'll just show you out from where did I get these values. You can see here 1.58, the baseline, 0.89 after 6 months, standard deviation of the first group, standard deviation of the other group. Clear? This is the data that I'm using, and I have entered it here. So I'll write calculate and okay, and calculate and transfer to the main window. Okay. After you do this, after the effect size is placed here, just say calculate. And your total sample size is 6. So anything above 6 you can take. Right? So minimum it should be 6. Now with the same example, I'll try to show you how it changes. Now I'm just converting from 2 tail to 1 tail. Okay, everything else is going to remain the same, and I'm saying calculate. Look at it now. The sample size is reduced. What will happen if I increase the power now? I'm going to make it as 95%. Okay, I want to be my study, very strong. And I'm going to say just calculate. Look at it. The sample size has increased. Now what I do, I am going to play a little with the effect size. The effect here is relatively higher, 1.58 and 0.89. What if it is not 0.89, but just 1.39? I am reducing the effect size. I am reducing the difference between baseline and post 6 months. I'm just reducing that. Okay. I say calculate and transfer, and here I look at it. Okay. So this is what I wanted to show, that whenever the difference is less, the sample size is more. Whenever the difference is more, the sample size is less. Right? So this is with respect to your paired t-test, and this is what you can actually get it also, everything written. Everything is there. You can directly take it and place it in your research articles or your synopsis wherever required. Right. So let us proceed. So what when there are two groups? Okay. When there are two groups and you are going to check the means between these two groups. So I'm very sure all must be thinking, oh, it is unpaired t-test. Yes, absolutely right. It's a t-test that we are going to apply. And the data that we are going to use here is this thing. Okay, the mean and the standard deviation. It is a relationship between oral health and demography in the elderly people. So they have given us the mean and they have given us standard deviation in men and women. Right? And if this is the same is the objective of my study. I'm repeating this continuously. This is the key article that you take for your research studies. So again, you just have to go here. So what's the next step? Go in test, go in means. Now, we are not checking for two dependent, but we are checking for two independent groups. Just click here and this particular thing appears. Okay. So the test family remains t-test, two independent group, a priori calculation, going for two test. Okay. Now we will enter the data. So what is the data here? Since I've already written here, so I know the data, I'll just make this to 80. The power is 80. The alpha error, I'm retaining it to 0.05 and I'm going to determine here. So the second one is a very convenient way. The first one, here the calculation, this particular calculation will ask you for pooled SD where you have to manually calculate. So let us avoid that and go for the next one. So you have to put the mean of the first, which is 38.5, and then mean of the second 36.04. Okay, standard deviation of the first is 7.263, and standard deviation of the next group is 7.01. Clear? So we'll say calculate and transfer, and then what we need to do, simple, just say calculate. So look, again, it makes sense, no? It's a descriptive study. So you have a larger. And again, if you change here, this allocation of ratio is same in both the groups, it says. Okay. So if you increase this, sample size will increase. Okay. So this is the total sample size, and this is per group. Clear? Yes. So we'll proceed to our next example, which is with respect to ANOVA. So where do we use ANOVA? Where do we use ANOVA? Which type of study design? Waiting for your response. If you respond, I can proceed. Great. Okay, more than 3 groups, right? So I have a small little example, so I'll leave it here. So it's a remineralizing potential of the 3 toothpaste on enamel caries. Okay. So we have here our groups, which is Colgate, Crest, and Incudent, and we are though it has a before and after, we are just considering the after. See, you can also consider only this, but for right now, for the particular calculation, I'm just seeing this differences between each group. Okay. So again, I go back to this. Now the test family is going to change. I am going to go with one-way ANOVA. Okay, this one. Many groups, one way, one independent factor. Clear? So I have selected ANOVA. Everybody got that? So out of the various ANOVAs, I've selected one independent factor ANOVA. So effect size, probability, power, we'll fix it this time to say 90. Okay. And number of groups. In the current study, we had 3 groups. Okay. Determine the effect size. Here you need to do a little bit of calculation for your own. You have to put here the number of groups. How many people per group? Since I know the study, there are 15 samples in that study that I just demonstrated here. We'll go back to it. Look at this. The present study is an in vitro study which was conducted on 145 sound extracted primary molar divided into 3 groups, that is 15 specimens per group. Okay. So go back again. Look at this. SD within each group. Now in this particular data, I have standard deviation for all the group, but I have to enter only one standard deviation. Are you getting that? Okay. So I can directly put from here all 15. That is the size of the group. Okay. So we have to calculate this. This we have to do manually or using your calculator. How? Let's see. This is the formula. Okay. So how many sample did group 1 had? 15. So we are going to take 15 minus 1 into standard deviation of the first group. Okay. That is 15 minus 1 is 14. Okay. Then is again 14 into standard deviation of the second group, the whole square. Then 14 into standard deviation of the third group square. Okay. This is extra. If you have fourth group, you can include that. And next is this, that is N1 minus 1. Okay. N1 minus 1 plus N2 minus 1 plus N3 minus 1 minus number of groups. Okay. So here it is 14 plus 14 plus 14 minus 4. Okay. So the first one I have calculated, that is 13.2 into 13.2, that is your S1 square, multiplied by 14, that is N1 minus 1. So same thing I have done for the other two groups also. Okay. And I have divided it by 14 plus 14, 28, 28 plus 14, 42, 42 minus 3, 39. Okay. So this all you add and you divide it by 39. Whatever you get, you have to square root them. And so this is the square root that you get. Is that clear how you're getting the pooled ST here? Okay. So we have got the pooled ST to be 14.56. Now let us enter it into here. So I'm writing here 14.56. Clear? So how much was the mean for the first group? See, just have a look at this, okay? It is 75.7. I'll just write it somewhere so that I can enter. It is 75.7, 78.2 for the second group, and 51.4 for the third group. Okay. So what was the mean for the first group? 75. Okay. 75.7. The mean in the second group is 78.2. And the mean in the third group is 50. 51.4. So it has transferred here and say calculate. Am I audible and clear? Because some people are saying that there is some internet issues. Am I clear?
Yes, ma'am, you're clear, ma'am.
Okay, thank you so much. Okay, so this is the way you have to calculate for ANOVA. That is whenever you have more than two groups, right? So here only calculation that is very different from the others is that's about your pooled ST, right? So I have dealt with the paired t-test, unpaired t-test, and ANOVA all being the parametric test. Pearson's correlation. Okay, when you are going to check the relationship between two things, okay, like dental caries and say frequency of eating sweets. When one increases, the other increases. So there is a relationship. That time we have to go for this. Again, the correlation value you can directly obtain from your key article and you can just enter here. Just go for test, correlation, bivariate, and you have to just put your correlation value. That's it. And it will calculate. Yeah. So I've restricted myself to the most commonly employed test here. Repeated measure ANOVA is the other thing. I am not covering the G power analysis for repeated measure ANOVA because the pooled standard deviation calculation is going to take us some time. Okay. But I'll just show you all how it has to be done. So go for means, go for repeated measures ANOVA within factors approach. Okay. And then you have to write here the variance. Okay. Everything remains the same. but you have to calculate the variance. If anybody is interested, please get back to me. I will send you my notes on that. Coming to the non-parametric test. So when they are not normally distributed, you go for a non-parametric test. When we are dealing with proportions, so most of the times it's like non-parametric version. So whenever we are dealing with proportions, we apply chi-square test. So here I have an example between association between type of delivery and dental caries. So normal, I'm just taking the prevalence of dental caries, so I'm directly going here. So normal delivery, you have 47.9%, and C-section, you have 56.4%. Okay. So again, 47.9 and 56.4%. Moving here, safe test. Now here you should not select the means. You have to select the proportion. Here I will go for two independent groups because C-section and normal delivery are not related to each other. They are different groups. So I go for this. It's very, very simple. You can select that you want the two tests. You have to just put the proportion here. You can put it even here and then say calculate. So it's, how much is it? 47.9 and 56.4.
Where I stop chi-square. I'll tell you what error I did and which it got this beeps. Okay, so coming to this test and test of proportion, and I am going for Fisher's exact test. Here, when I am putting the proportion, we are supposed to convert it into points. Okay, so now converting into points, I will, okay. Give it as 0.47 for first group, and the second group is 0.56, which is 56% and 47% respectively. And the ratio between both the groups are same, and I just say calculate. Clear? So this is how you do when you are applying chi-square. So similarly, when you have I have a little rush. Okay. When you have Wilcoxon sign rank test, again, it's a non-parametric version of your paired T test, right? How are you going to identify? By knowing the standard deviation. If the standard deviation is more, that means it's a non-parametric distribution or a non-normal distribution, right? So that time, if you have a single group, you are going to apply Wilcoxon sign rank test. And when you have a two groups, you are going to apply the Mann-Whitney test. Clear? So here, you can directly go for test, go to means, because now we are talking with respect to means. Now here you have to remember, even if it's a non-parametric or a non-normal distribution, the means will be provided in your key article, right? So for a single group, you are going to go for one group. For this, two dependent groups. Okay, not one group, you have to go for two dependent groups. And when you have two groups, that is your Mann-Whitney test, which is also known as independent group Wilcoxon test. Clear? That's the only variation. And everything remains the same. Okay. Apart from one thing, that for non-normal distribution or non-parametric test, you will get this thing a little different. Parent distribution. You have to say what is the parent distribution. Obviously, it's not normal. We are going to select min ARE. It's a different technique of calculating power analysis for a skew distribution. Okay, it is called as min ARE. Right, so just select that. Everything else remains the same. Everything else remains the same. So min ARE stands for asymptotic relative efficiency. Asymptotic relative efficiency, which is an adjustment for power analysis in a skewed distribution. Right? So same thing you are going to do for your, this one is for two groups, for a single group also similar type. Clear? Now you can see you are getting here the name as Mann-Whitney test. Now, if I talk about the three group, the counterpart of ANOVA, that is your Kruskal values, but there is no mention of Kruskal values here. So what next? How are you going to calculate? You are going to calculate as your ANOVA only. Okay. One dependent ANOVA, but you are going to apply a correction factor. Whatever sample size you get, you have to add up 15% extra of that sample size. Do you get? So if you have calculated 100 in ANOVA for a non-normal distribution, you add extra 15 subjects to that. So your sample size is going to become 115. I repeat, for Kruskal-Wallis, which is a non-parametric test, you have to add 15% of the sample calculated in ANOVA. So Mann-Whitney is a non-parametric test when you have two groups. Non-parametric version of ANOVA is Kruskal-Wallis. Okay, you are going to add here 15% extra subjects. Coming to prevalence studies, that is just now somebody who had messaged me about the prevalence study. So how are we calculating the prevalence study? Calculation of sample size for observational study. Yes, observational studies includes your observational studies includes your cross-sectional studies, analytical studies. Okay. So coming to the prevalence study, the formula here is Z square P into 1 minus P divided by D square. Okay, there's a short form for this also, 4PQ by L square. That's what we also have this formula like this. The Z is the Z statistics for the level of confidence. It depends on what level of confidence are you fixing. For 95% confidence level, the value, this is a constant. So don't think how it has been derived. Okay, it's 1.96. Clear? If you are having this as 98% confidence, then it is 2.326 and so on. So that you have to fix. Rest everything you will get. P is the prevalence already. Okay, I'll give you here an example. If I want to check the prevalence of COVID-19, okay, prevalence of COVID-19 in say Madurai city. So I have to get a little bit of data. How much prevalence is there in Madurai? How can I get? Either through a pilot study or from any other source of data. Clear? Or any other source of data even in the nearby districts, if I can get, saying that same prevalence I'm expecting even in Madurai. Clear? So that is your P. So 1 minus P, whatever, like if I say the prevalence is 60%, so P will become 0.6. And this is 1 minus 0.6, which is 0.4. Is that clear? The D square is how much of error am I allowed, or how much of error I am allowing in my study to occur. Like say, if I calculate the prevalence in my study as 70%. So what's the error that would have happened? Plus or minus 5%. This is the maximum error that can be permitted for an observational study. That is what you have to fix here. So 5% is 0.05. So just substitute. Here you have to put 1.96 into 1.96, which is somewhere around 3.8 odd. That's why we round it up to 4. Okay. P is your prevalence, which whatever is the prevalence you are going to add here, that is say 0.6. 1 minus 0.6 is equal to 0.4 and the D is 0.05. So 0.05 into 0.05, that is 0.0025. Okay. If you just substitute all of this, you can get the sample size required for your prevalence study. Clear? So it's nothing but 4 PQ by L square. Yeah. So see the example here. Survey of anemia in children under 5. Assume the prevalence of anemia is 40% and error that you are allowing is so much. So I've just substituted and this is the sample size. Yeah. Okay. This was the time that I had actually decided to give you all a break, but let's continue. Okay, the query, what about the sample size in animal study? See, animal studies are actually clinical trials, right? How much of difference you are seeing? What happens in animal study when you're trying to calculate the sample size, because it is in a controlled environment, your standard deviation is anyway going to be very less. In your in vitro study and in animal study, your standard deviation is very less, because everything is a controlled environment. So the sample size will generally be calculated smaller. So moving to the next part of the presentation, which is about the different sampling techniques. Okay, I spoke how much to take. Now, how are you going to retrieve this into your study? If I've decided my sample size is 100, how am I going to collect this 100 samples in my study is about the sampling technique. In this, we have two types of sampling technique. One is the probability sampling and other is non-probability sampling, which is also called as random and non-random sampling. Okay. Random advantage, everybody can just be selected. Everybody has an equal opportunity. A small little example, when I go for a final year class, I can just pick up students by calling out their roll number randomly. So everybody will be, kind of alert. What if I call out the names of only those people whose names I know? So obviously people whose names I don't know will be totally relaxed. Okay, anyway, ma'am doesn't know my name, so let me be relaxed. So that time they don't have the equal opportunity. So that is a non-random sampling. And when I'm just randomly picking up the numbers, roll numbers, it is a random sampling. Clear? Under random sampling, we have all these various things, which is the simple random, systematic random, stratified, cluster, multi-phase, and multi-stage. Under non-random or non-probability, we have quota sampling, purposive, convenience, snowball, and self-selection. A point of advice here, whenever we go for a non-probability sampling, the interpretation of your results is questioned. Okay, whether it can be applied to the entire population. Okay, but when you do a random sampling, obviously your study is much more stronger. So that is what it says. Generalizability is better. The first one is simple random sampling. Simple random sampling can be done in two methods. One is you just make chits. Okay, you just make chits of number of students in your class and you just pick up whatever number you need. So this is the lottery method. The other is you can always use a table of random numbers, which is available on net and even in textbooks. There, what you need to do, you have to just close your eyes and keep your finger on any number. And from there, you decide whether you want to go vertically down or horizontally. Okay, it's just a paper with a lot of numbers written. So say if your population is 700, so you can include the first three numbers. Okay, so that is about a random list of random numbers. And again, whenever you're doing using this list of random numbers, the numbers need to be allotted to the people like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. And so whenever you're calling out that number, that particular person will get included in the study. Next, moving around with systematic random sampling. Here, you have to do a little calculation. That is, you have to determine the kth item. Okay, which is determined by dividing the number of samples you need divided by the total population. So if my total population is 100 and I just need 10, so I divide and I get 10 as an output, right? So how do I start about, say again, we'll retain our example to a classroom. So the first number I will pick up randomly, say 4, 5 or anything so. So let it be 7. So my next number is going to be 7 plus 10. Next is 17 plus 10. Next is 27 plus 10 and so on. Okay. So that is about systematic random sampling. Moving ahead with the stratified random sampling. Stratified random sampling includes that the entire population is divided into different strata. Why do we need? For example, again, your dental college, not yours, but our dental college where we have 80% girls and 20% boys. So if I want to have the equal representation of the general population, even in my sample, I'll keep 80% girls and 20% boys. Okay, this is stratified random sampling. Once you divide and you assign a proportion, that so much proportion, and then you have to do random selection. That is very, very important. Okay. Moving ahead with cluster random sampling. Clusters means they are naturally formed groups. Okay. Naturally formed groups like villages, schools, wards, blocks, hospitals. All these are naturally occurring groups. So instead of picking up one person, you are going to pick up the clusters there. Okay. So you are going to randomly select the villages, randomly select the schools, not people from the school. So this is about cluster random sampling. The next one is the multi-phase sampling. The multi-phase sampling includes that a data, say if you're doing a tuberculosis survey, okay? So you're trying to see how many of them have tuberculosis. So you do first a Montex test. So only those who are positive with the Montex test will produce with the X-ray. And only those who are positive with the X-ray will go to the next step. Right? To avoid obviously the resources that we have. So multi-phase test is a part of information is collected from the whole sample, and then the detailed information is collected from limited samples. Clear? So we have completed with this fifth type. This is the fifth type of random sampling. So previously we have covered with the simple random, the systematic random, stratified, and cluster, and this is the fifth one, which is the multi-phase. The last one under random sampling is multi-stage. Especially it is taken up when you are doing a national level survey. Okay, so if I want to see, say, prevalence of XYZ in India, so I have to randomly select the states. From the states, I will randomly select the districts. From the district, I will randomly select the cities. From the cities, I'll randomly select the blocks. And from there, I will randomly select the households. So it goes in the stepwise. So this is at a different stage you're sampling people. So it is called as multi-stage sampling. So right now we have just completed with the random sampling part. Moving about with the non-probability sampling or non-random sampling. Most of the times it is used in qualitative research. Okay. Here there is a lot of chances of getting into bias. So whenever you're generalizing the result, you have to be careful when your sample selected is a non-random sample. The first one under non-random is your convenience sampling. It is based on convenience of the researcher. If I want to do, say, some test on some kind of mouthwash, which is really bad to taste, I will obviously select my own students and do on that. Now this is very convenient because they are going to listen to me. Okay. So, but I cannot extrapolate this result to the general population. Okay. So this is a drawback. There are few times that convenience sampling you are allowed to do, but as I said, it comes with an error. Okay. It is like a time-saving mechanism. Instead of going and researching a lot and getting things, you are just getting, reviews from your friends and finishing off. Quota sampling. Now, here I would like to emphasize that there is a very slight difference between quota sampling and your stratified sampling. Same, the first step is going to be the same, that you are going to create stratas. Okay. So you're going to create different stratas. That is nothing but quota. So much of 80% I'm retaining for girls, 20% I'm retaining for boys. But under quota sampling, how you're going to recruit is going to be through the convenience or a non-probability sampling. Okay. But whereas in your stratified sampling, you're going to use the random sampling technique only. Okay. So this is the minor difference between the quota sampling and stratified sampling. First step is the same, that you're going to stratify. Okay. So 80% I'm going to reserve for girls, 20% for boys. But how I'm going to select that 20% is what is going to make the change. Next is purposive sampling. It depends on the purpose of research. Like whenever the disease is rare, obviously you cannot have random sample. That is the purpose of the research. When a disease is like, say, 1 in 1,000, 1 in 10,000 or so on, you cannot really go ahead with a random sampling. You have to do purposive sampling. I need only these people in my study. It is based on the purpose of the research. Okay. So where it can be used, typical cases, deviant cases, critical case sampling, when there is a lot of heterogeneous group involved, you go ahead with the purposive sampling. The second but last one is your snowball sampling under non-probability sampling. Snowball, the name itself says, when the snowball rolls, when it rolls, there is a lot of ice that gets again coated over it. So same thing, I go to one person whom I identify. For example, if I'm doing a study on smokers. Okay, so I identify one person who is a smoker and ask them, do you know somebody else who also smokes? Right? So he will give me a reference of his one friend. I go to him. Then I'll ask him, do you know anybody else? He may give a reference to his colleague. So I will continue this way. It is kind of referencing. The drawback here is only those who are related to the first person will have a chance to get included in the study. Okay. Again, this is good sampling technique for rare diseases. The last one in the row is self-selection. Self-selection is just ask who wants to be in my study. So people who ever volunteer, you can just pick them up. So this is also a type of non-probability sampling. Okay. So here with this, I am ending with the sample size calculation and the sampling techniques. I think I'm on time. Yeah, I have reserved 10 minutes for the question answers. Okay, so here I wind up. I thank my college, my management and the department staff, and obviously my postgraduate students for continuously supporting me through making of the slide and collecting the information. Yeah.
Now I take the honor in presenting the certificate of appreciation to our guest speaker, Dr. Sangeeta ma'am. Thank you very much, ma'am.